All right, we're going live. So if you do have an AP exam over the next 2 weeks and you're missing class, just know that I'll put all these videos into the shared folder. You know where to find them. Hopefully the microphone doesn't randomly go out at the end for no reason. But if so, you know where to find me. I very seldom leave this room, right? Anyway, here we go. We got the tangent of x equals cotangent of pi halves minus x. That's the cofunction identity. Tangent of an angle is equal to cotangent of its complement. Can't prove it, as I said, yet, but we can sure verify it. So here's the notation. If you're picking an angle like pi 6, you could just say pi 6 colon or at pi 6 colon, and that's the at symbol, in case you, isn't that really good? It comes from a round, right? Around. See that? Around. I'll be there around 5. It's an A with a roundabout. A round, but it's the at symbol. There you go. Pretty cool. Pi halves, okay, pi 6, sorry. So you plug it into the left, you plug it into the right, and now you draw a line down the middle. The reason you draw the line down the middle is because you don't want to cross-contaminate. While you're proving or while you're verifying, you cannot bring something from one side to the other or multiply both sides by the same thing or subtract something from both sides. You have to treat each side as its own independent expression, and you work down until the bottom lines of both are either the same or they're not the same. Now you're going to know in advance if something is truly an identity or not an identity. Okay. If I ask you to find a value that shows that it works for several, then you know it's going to be an identity. But just because it works for pi 6 and 7 pi fourths in general, that's not going to mean that it works for all of them, right? So this is called verification. If you tell me it's raining outside, right? I can look outside this window and see that it's raining outside this window, and I can look outside that window and see if it's raining. So can I then say, yeah, it is raining outside? And I call my wife and say, hey, honey, it's raining outside. And she looks out her window and she's like, no, it's not. And I'm like, oh, I forgot to check your window. No amount of verification constitutes a proof. That's what I'm getting at, right? No amount of verification. That's just plugging in individual values and getting the correct answer every time. That doesn't mean that's not a proof mathematically. Proof is a lot harder. To prove something, you got to show that it works for all values. And remember, to do that, you have to use variables. But proving this one requires what's called a composite identity, which is in the next section. So right now we'll just verify. We'll be content. And this is good too, because we get to review unit circle time, right? Everyone look at your watch. What time is it? It's 11:11. Make a wish. I wish all the kids will do their math homework and pass their AP exams and do well on finals and have a safe summer and a very prosperous rest of their life. Did I say it out loud? Will it come true? I said it again inside without saying it out loud. So now it should work. And it's still 11:11. So I got it in there. All right. Yeah. All right. So anyway, look at your watch. It's now 11:12. It's unit circle time. Every time is unit circle time. What is tangent of pi 6? That's right. Square root of 3 over 3, right? Very good. Very good. Square root of 3 over 3. Hey, now just to review 5.7, what if I started you with square root of 3 over 3, but I put arctangent in front of it? What is the arc or inverse tangent of square root of 3/3? Pi over 6, right? Because tangent of pi 6 is square root of 3/3. Arctangent of square root of 3/3 is pi 6. All right, so we come over here, and now we need to get a common denominator, or can we distribute like that? Did anyone distribute the cotangent? You actually can't do that, so good. You can't distribute. You can't distribute. If that were a natural log, you couldn't distribute. In general, you can't distribute a function inside of itself. Okay. Now, let's just get a common denominator here. The common denominator is 6. So pi halves is how many pi 6? 3 pi over 6. So 3 pi over 6 minus 1 pi over 6 is 2 pi over 6. And that simplifies to what? Pi thirds. Yeah. And now look at your watch. It's unit circle time again. What's cotangent of pi thirds? Square root of 3/3. Yeah. Now, because this is verification and not proof, you don't put QED at the end. You don't sign your name there. It's not that huge of an accomplishment. What we typically do is we just put a check just to verify that the left side equals the right side. So here's what we know. We know that the cofunction identity for tangent works for all values that are pi 6. Right? All of them. If it's pi 6, it works. What'd you do? Yeah, it does. No, don't turn it into tangent. No, because then that's kind of proving the identity to prove the identity. Yeah, so don't do that. No, don't do that. Okay, now let's do the same thing for 7/4. We'll say at x equals 7/4, colon. We plug in the left, we get tangent of 7/4. It was part B, yeah. And I want to show, yeah, I'm telling you which values to use here. So if that's why it didn't make sense, that's why. I'm telling you to use these two different values. Okay, but now we work down, and again, the left side should equal the right side. We want to work them independently. What is tangent of 7/4? It's unit circle time, baby. I know this one. Quadrant 4? -1. Very good, because it's negative √2 over positive √2. It's -1. Now on the other side, we need to get a common denominator, which is 4. So pi halves is 2/4. 2 minus 7 is -5/4. And now you're like, Jiminy Crickets, cotangent of -5/4. Well, there's 3 ways to go from here, working straight down. Number 1, you could just say, oh, in your head, -5/4 lives in which quadrant? If I have to rotate clockwise, -pi halves, -pi. It should be over here in quadrant 2, right? Yeah. And what is the then x coordinate there divided by the y coordinate? -1. So that's one way to do it. Or here's another way to do it. You could say, oh, -5/4, that's coterminal with which one? It's coterminal with infinitely many, but what's the one that's between 0 and 2 pi? 3/4. Okay. Now you can't say that -5/4 equals 3/4, but their cotangent ratios sure do, right? Because coterminal angles have the exact same trig ratios. And now you can be like, I just prefer the look of that one. Cotangent of 3/4 is -1. So that would be the second way to do it. Or you could even do it a third way from there. Is cotangent even, odd, or neither? Odd. Cotangent's odd. Remember, the only 2 evens are what? Secant and cosine. Good. So remember, if an odd function has a negative input, do we just forget about it, or do we bring it out front? We bring it out front. So that's the same as negative cotangent of +5/4. That's using the even odd identity. And now you're like 5/4, that's over here in quadrant 3. Bring down the negative. What is cotangent of 5/4? +1. Good. Times the negative that you brought out front, -1. That's 3 different ways to think about evaluating that, right? We have options now, but the fact remains, does -1 equal -1? Go to that and see. Yes. So we now know that we can use this identity for pi6 and 7/4. And as it turns out, once we prove it with the composite identity, it works for all angles in the domain. So as long as you get an output on both sides, it's going to be the same number. If it doesn't work on one side, because you know cotangent and tangent do have discontinuities, like pi halves, that doesn't exclude it from being an identity. All right, it's true for all values in the domain. All right, now I said proof was kind of hard, but to disprove something can sometimes be easier, because to prove something is true, you need to show it's true for all values. But to show that something's false, you just need one counter example, we call it. All right. So if you look up here where the dictionary and all this stuff is, this is a counter example, right? But that's 2 words, counter example. This is a nice beige laminate that goes well with the blue floors. And you know, it's just one option that you have for your own countertop, right? It's a counter example. Yeah, thank you. This is a counter example, one word. So what does counter mean in this context? Like a counter argument. Go against. Good. So a counter example is an example that goes against the claim that something's an identity. That's what a counter example is. And you can have an expression that you have verified, or an identity that you verified that you think's an identity, and you could have verified it for like millions and millions of values. But that doesn't mean it's true, because someone can come along and find a single counter example to disprove your theory. That's all it takes. Okay. One counter example that shows something is false means that it's no longer true, even if it works all the other times. That's the high burden of proof we have in math. It has to work all the time, or if it doesn't work all the time, it's just a conditional equation now. And it may have infinitely many solutions, but it's not an identity. Okay. So we've already had this idea because earlier in the year when we were reviewing our algebra rules, we had this: find a counterexample for the square root of x squared plus y squared equals x plus y. First of all, does anyone here have an itch to say that's an identity? Take the square root of x squared plus y squared, boom, square root of x squared, square root of y squared, add them together. No, not anymore, right? But maybe when you came in after last summer, you're like, yeah, that's true. I do that all the time. Now, if they were multiplied, it would work, right? X squared times y squared square root is xy. Because remember, the difference between factors that are multiplied versus terms that are added or subtracted. These are terms. So this is not true. So your job is to find a counterexample, right? So let's try x equals 0 and y equals 1. Let's see what that does. Colon, right? Draw a line down the middle. We get the square root of 0 squared plus 1 squared. That's the square root of 0 plus 1. That's the square root of 1, which is 1. Now remember, when you're doing a proof or verification like I'm doing here, the process is the product. Every line is what we need to see. So when in doubt, do not leave it out. This is the one time where you don't want to impress someone with what you could do in your head. Rather, you want to lay the steps brick by brick so the person can walk on it when they shuffle their feet, not even take a step over a gap. When in doubt, don't leave it out, okay? And now I plug it into the right side, and I get 0 plus 1, which is 1. 1 equals 1, boom. Mr. Corpy, this thing is an identity because 1 equals 1, right? So next time I see x squared plus y squared with a radical over it, I'm just going to call it x plus y. You okay with that? No, I'm not okay with that. I do see that 1 equals 1. So really, the way things work in the real world is when you have something that you think is an identity, you think it's a theorem, you either have your peers evaluate it and say, yeah, we can't find any flaw in your logic, or you just, one person comes along and says, but actually, did you ever try? So you're going to know in advance if something is an identity, and I'm going to ask you to prove it later on, or in this case, something is not an identity and you find a counterexample. You're going to know in advance if it's supposed to work or not. It's supposed to not be an identity. So if you pick numbers and it does work out, guess what? You've just found one of the conditional solutions. Try again. Now, don't erase this. Maybe keep it off to the side as a successful example of something that failed for what you're trying to do, right? You didn't fail, you just successfully did not achieve. So you should choose values that are different than just 0, 1. You should choose like big positives, negatives, fractions. Let's try this. I'll help you out. X equals 3 and y equals 4, colon. Okay, so we draw the line down the middle, and here we go this side here. 3 squared plus 4 squared. That's 9 plus 16, 25, 5. See, you show every step. And I chose those because it's a nice Pythagorean. That's all, folks. Nope. Pythagorean triple. What is wrong with me? Don't answer that. Don't answer that. I'm not looking for suggestions. Okay. I'm afraid I don't want to hear the truth. Let's plug it in on this side. 3 plus 4. 3 plus 4 is a 7. Whoa. And now you're like, what in the 5 equals 7? Is that true? No. So you don't do this. You don't put a not equal sign there. What you do is you draw this symbol down at the bottom. That arrow ramming into that arrow. What does that symbol mean? Crash, right? 2 rams butting head. I don't know if you're paying attention to the video on Friday, but that's what we do when we have a contradiction, right? When you have a contradiction, that is the symbol for it, okay? So that's what we write at the bottom. And that's kind of our word to other people saying, hey, don't try this, it doesn't work, okay? 5 doesn't equal 7. Now, yeah, there are values of x and y that make it true. X could be 0, y could be 1, x could be 1, y could be 0. They could both be 0 and it would still work. But if it doesn't work for all, it's not an identity. It's not an identity. All right, so anyway, let's do it with trig now. You have sine of the angle, x plus y. We call that a composite angle. That angle is composed of 2 other angles, x and y, by adding them together. You are going to see something like this quite often when we get into the subsequent sections, and you might have the urge to distribute it in. But can we distribute a sine into its own angle? No, like the natural log of x plus y is not ln of x plus y. So in general, you can't distribute a function inside of itself. Now, someone asked at the end of class last period, why can't we do that? But if this were sine of x, if it were sine of x times the quantity x plus y, then you could distribute. You could say sine of x times x plus sine of x times y. That's fine because we're multiplying the entire ratio inside. So that's the difference between sine of x times x plus y versus sine of x plus y. X plus y is now inside, so you can't distribute. So let's prove that. Let's choose some angles from the unit circle, any of them. Anybody got some unit circle angles? Pi. Whoa, there's a bag. I saw it. Pi and 2 pi. Okay. Let's let x equal pi and y equal 2 pi. And we'll give it a go here. So we get sine of pi plus 2 pi. That's sine of 0 plus 0, which is sine of 0, which is 0. And over here we get sine of pi plus sine of 2 pi, which is 0 plus 0, which is 0. Ah, I guess it does work. I guess you can distribute inside. Does that mean it's an identity? No, you're going to know in advance it's not an identity. So if you happen to choose values that make it work, just choose others, right? Yeah, when you're choosing values, try not to choose like the special cases. The quadrantal angles are special cases, really. They're just zeros and ones. So I would choose something from the interior. So let's see, x equals, what'd you say? 7 pi fourths, and then someone else choose another one for y. Don't choose another pi fourths angle. Choose a pi 6. Good. Let's just do pi 6. So let's try it now. We get sine of 7 pi fourths plus pi 6. And then we draw the line down the middle, and that's sine of 7 pi fourths plus sine of pi 6. Okay. Now this is going to be fun over here. I got to get a common denominator. What's the LCM of 4 and 6? 24 would work. Their product is always a CM, but the LCM would be 12. Yeah, so I'm just going to put them all over 12. So for the first one, I got to multiply by 3 over 3. Yes. So it becomes 21 pi. Plus, to get from 6 to 12, I got to multiply the second by 2 over 2. So that's 2 pi. Okay. So this is why these are fun. Now 21 plus 2, that's 23 pi 12ths. Holy crap. Does that simplify that angle? Oh, that's 7 pi fourths. 3 times 7 is 21 times 2. Oh, yeah. We can't figure that out, can we? 23 is prime. We tried. Well, let's do this. It didn't end up being on the unit circle, but is that going to be positive or negative? Where does 23 pi 12 live? Are you sure? 23 pi 12? Quadrant 4. One rotation would be 24, right? Yes. So it should be right there, like you said, quadrant 4. So it should be positive or negative? If it's sine, it's below. It should be a negative number. And should it be big or small? Should it be closer to 1 or closer to 0? Sine, y, height. If we're close to the x-axis, the height should be what? Big or small? Small. So this should be a really negative small number. So we can't get the exact value, but I know it's a negative small number. Let's try over here. That might be enough, right? To convince us at least. Sine of 7 pi fourths. That's negative square root of 2 over 2, right? Sine of pi 6, positive 1/2. And so if I add them together, I get negative square root of 2 plus 1 all over 2. Well, that's also going to be a negative small number. So guess what? We found, I think they're going to be different, but I can't tell for sure without a calculator. So again, we have to try finding different values, right? Something that we can actually get down to comparison. So put this off to the side. All right, we're collecting things that don't work. Right, you'll know ahead of time. Yeah, because otherwise it's real frustrating. Yeah, but you'll know in advance. In this case, it's not supposed to work. So let's choose some different values. Let's try. Yeah, if we try, once we brought in the pi fourths, you see that we were getting denominators that were unhelpful. So now you might be like, oh, let's try the pi 6 and the pi thirds, right? So you live and learn, right? You're learning from your mistakes. You're modifying what you're choosing here. So that's sine of pi 6 plus pi thirds over here. And this is sine of pi 6 plus sine of pi thirds. Okay. Now this should be easier to combine because now the LCM is 6, right? So if I just multiply pi thirds by 2 over 2, I get 1 pi 6 plus 2 pi 6, which is 3 pi 6. And 3 pi 6 simplifies to what? Pi halves. Yeah, so that's going to be nice now. Sine of pi halves is what? 1. Okay. Now let's look on this side. Sine of pi 6 is a half. Sine of pi thirds is square root of 3 halves. So when I add those together, I get 1 plus the square root of 3 over 2. Huh. Is 1 plus the square root of 3 over 2 equal to 1? No. I don't know what it's equal to as a decimal, but I sure know it's not equal to 1. Okay, because 1 plus the square root of 3 is not equal to 2. So now instead of putting a not equal sign, we'll put the contradiction there. So that one took a little bit of effort to find, one, that A didn't work, and then two, something that worked in a way we could use without the unit circle, from the unit circle, sorry, without the calculator. So there it is. Now we have found that that is not an identity. It doesn't work for any of the trig functions. So later on, when you see something like cosine of A plus B, it's not cosine of A plus cosine of B. Got it? All right. Now let's look at this one here. Part C, cosine of X plus sine of X equals 1. Is that Papa Pid?
No, it's not.
Oh, why is it not, Schreiber? You're right, it's not.
It's not.
It's missing. What does the P in PID stand for? Pythagorean, right? And Pythagorean is A squared plus B squared equals C squared. Or for us on the unit circle, X squared plus B squared, sorry, Y squared, is R squared. It doesn't matter what you call the variables. What's important though is that they're what? They're squared, right? So cosine squared of X plus sine squared of X equals 1. And that is an identity. It works. Now, if you're proving or verifying, you have to draw a line down the equal side and you can't cross-contaminate. But once you know it's an identity, you could put any version of it you want. So for instance, I could subtract sine squared from both sides. I can get cosine squared is 1 minus sine squared. Okay, I can bring the sign across. That's going to work. Okay, but what if I took the square root of both sides? The square root of cosine squared plus the square root of sine squared, and I took the square root of that side. Isn't that just cosine of X plus sine of X equaling 1? No, because is that right there equal to that? No, we just disproved that on where? Part A. X and Y don't have to be numbers. That X could be cosine and Y could be sine. So that doesn't work. So these have to be squared in order to be Pythagorean. It's not. So I would tell you to find a counter example. So let's draw a line down number 1. And we only got to choose one angle here. I would stay away from quadrantal angles because that can be dangerous. Might have to do more work. Pick something from the interior, like what? Pi 6 I heard first. So you could choose a different one. So that's cosine of pi 6 plus sine of pi 6. And if I evaluate, that gives me square root of 3 halves plus 1 half. And again, that's the square root of 3 plus 1 all over 2. And the right side is a 1. Are those equal? No, they're not equal. Okay, boom. But notice this. Notice this. Had it been cosine squared plus sine squared equal 1, and I plugged in, that would be the square root of 3 halves squared plus 1 half squared, right? And let's see what that gives me now. That gives me the square root of 3 squared, which is 3, over 2 squared, which is 4, plus 1 squared is 1, and 2 squared is 4. And so 3 plus 1, I get 4 over 4, which is what? That is 1. So I would have verified the Pythagorean identity. Notice how important the squaring is to that, right? In order for that to equal 1. So you got to be careful, read carefully, and memorize your identities. The better you have them memorized, the more easily you can not only recognize them as options, but you can look at different versions of them like that. That's kind of the version that we typically use the Pythagorean identity in. Cosine squared is 1 minus sine squared, or sine squared is 1 minus cosine squared. Okay. All right. So that's counter examples, finding something that you know in advance is not supposed to be an identity. You just got to find some values and demonstrate that it doesn't work. And you work straight down either side. When they're not equal, put your little contradiction sign. All right. We're going to pick up with example 6, I guess, tomorrow. Is class already over? Yeah. Time flies when you're doing math.
Which ones on the homework are like the ones?
If it says to verify or to find a counterexample, yeah. If you read the homework and it says to verify or find a counterexample, you know that you could do that. Starting with example 6, though, that's where we start getting into the mechanics of what we're going to be doing when we prove things. All right. Y'all can get a head start by a couple seconds. Have a great day. We'll see y'all Wednesday. Seniors report to the auditorium tomorrow. During 6.